In our very first episode, we told you the good news about asteroids. We've mapped most of the big ones. We tracked them for years, sometimes decades. And in 2022, we proved we can actually nudge one off course. Comets are the same physics, wearing a very different clock. A long-period comet can spend thousands, even millions of years in total darkness beyond the edge of the solar system. Invisible, frozen, giving off no light of its own, before something finally pulls it sunward. By the time it's bright enough to spot, it may already be months from arrival, not years. And when it does hit, it hits harder, because comets move faster than almost anything else in the solar system. So here's the question this episode has to answer honestly. When the warning window collapses from years to weeks, does the survival plan collapse with it? Or did we already build something that works either way? Welcome back to Space Won't Win. We've deflected an asteroid, braced for a solar storm, outlasted a beam with zero warning, watched a star for decades before it could hurt us, and found a way to detect the invisible. This episode takes everything from video 1 and asks it to work under pressure, with a fraction of the time. If you haven't seen the asteroid episode yet, go watch it first. You'll want that foundation, because we're about to build directly on top of it. Subscribe now, because this is the episode where the clock actually matters. Let's get into it. An asteroid is a chunk of rock and metal, usually orbiting the sun on a predictable repeating path we can track for years. A comet is different at almost every level. Most long-period comets originate in the Oort cloud, a vast frozen shell of icy debris that surrounds the entire solar system, some of it nearly a light year from the sun. They spend the overwhelming majority of their existence out there, in total darkness, doing nothing that a telescope could ever detect. Then, occasionally, sometimes triggered by the gravity of a passing star, sometimes by nothing we can identify at all, one of them gets nudged onto a path that finally brings it sunward, and it can be on a collision course with the inner solar system for the very first time in its existence, with no prior orbit on record for us to have ever noticed. Here's the detail that defines this entire episode. A comet is essentially invisible until the sun starts heating it. That heating vaporizes surface ice, releasing gas and dust that catches sunlight and forms the glowing coma and tail we associate with comets. And that's usually the first moment it becomes bright enough for our telescopes to pick up at all. Which means, unlike a rocky asteroid that reflects at least some sunlight throughout its entire orbit, a long-period comet can go from completely undetected to a confirmed threat in a matter of months, simply because that's when it started being visible in the first place. And when a long-period comet does arrive, it typically moves faster than a typical asteroid. Some approach at more than twice the speed because they're falling in from so much farther out, picking up enormous velocity under the sun's gravity the entire way down. Higher speed means dramatically more kinetic energy on impact for an object the same size. In 1994, we watched this play out in real time when Comet Shoemaker-Levy 9 broke apart under Jupiter's gravity and slammed into the planet in more than 20 separate pieces, leaving scars in Jupiter's atmosphere larger than Earth itself. That wasn't a simulation. That was a live demonstration of exactly what this category of object can do. So, let's be honest about the number, because this is the episode where the warning time genuinely shrinks. For a long-period comet on its first ever trip through the inner solar system, realistic estimates put our warning time somewhere between a few months and about a year, occasionally less, if the comet's approach angle keeps it hidden from ground-based surveys until it's already close. Compare that to an asteroid, like the ones we discussed in video 1, where decades of advance notice is often possible. This is a real, meaningful downgrade in preparation time, and pretending otherwise wouldn't do you any favors. The good news is that the same detection infrastructure from video 1, Catalina, Pan-STARRS, Atlas, and eventually NEO Surveyor, is already watching for exactly this. In 2014, Comet Sighting Spring was discovered over a year before it swept within 87,000 miles of Mars, close enough in cosmic terms to have been catastrophic had Mars been in Earth's position. That's real precedent. A long-period comet, discovered with more than a year of lead time, tracked precisely enough to know it would miss. The system isn't starting from zero. It's starting from a shorter runway. And a shorter runway changes the checklist, not the plan. With less time, the priority shifts almost entirely toward the fastest, most proven option in the planetary defense toolkit, because there's no time left for the slow, gentle approach. Which brings us to the part of this episode where Video 1 stops being a reference and starts being a lifeline. In Episode 1, we walked through 3 deflection tools: the kinetic impactor, proven in 2022 against the asteroid moonlet Dimorphos; the gravity tractor, a slow, patient tug that needs months or years to work; and nuclear standoff deflection, the last resort for the shortest timelines. A Comet scenario immediately eliminates one of those. The gravity tractor needs time we almost never have with a first-time long-period comet. Its gentle, persistent pull only adds up to something meaningful over many months of continuous effort. That leaves the 2 faster tools to do all the work. The kinetic impactor still works exactly the way it did against Dimorphos, but the math changes. With a decade of warning, a small nudge compounds into a massive course correction by the time impact would have occurred. With a matter of months, you need either a much larger impactor, a much faster intercept, or multiple missions launched in rapid succession to stack enough deflection into the time remaining. This is exactly why space agencies have spent the years since DART designing follow-up missions and rapid response launch capability. Not because they expect a Comet scenario tomorrow, but because a fast-arriving comet is the specific case that demands it. Here's the part that should genuinely reassure you. The hardest problem in planetary defense was never the physics. It was proving the physics works at all, and proving we could build, launch, and precisely target a spacecraft fast enough to matter. DART already answered that question. The vending machine-sized spacecraft that hit Dimorphos in 2022 shifted its orbit by 33 minutes, more than 10 times the minimum needed to call the test a success. A Comet scenario doesn't require inventing a new capability. It requires having that capability ready to launch on short notice, which is precisely the argument planetary defense scientists have been making for funding rapid response missions ever since. The technology exists. The remaining question is readiness, not possibility. And the core rule from our very first episode applies here more than anywhere else in this series. The earlier you act, the less force you need. With a comet, that rule stops being a nice-to-have and becomes the entire strategy. Every additional week between discovery and a launch decision is a week of deflection you don't have to manufacture through brute force. That's why the true defense against a fast-moving comet isn't a bigger rocket. It's a detection network fast enough and a launch system ready enough that the early part of Act Early survives even when the warning window shrinks. If deflection isn't possible in time because the comet was simply too large, discovered too late, or the intercept missed, ground survival follows the exact same physics we covered in Video 1. Because a comet impact and an asteroid impact release energy the same way once they reach the surface. The sequence is identical. The flash of light arrives first, faster than sound, brighter than the sun. Look away immediately if you see it. The heat pulse follows within seconds. Cover exposed skin. Put solid material between yourself and the direction of impact. Then the shockwave arrives, sometimes minutes later, and that gap is your entire survival window. Get underground. Get behind concrete. Get to the lowest floor of the strongest building available. The one meaningful difference from Video 1, because comets typically hit at higher speeds, an object the same physical size as an asteroid releases significantly more energy on impact, which means the damage radius, the shockwave range, and the distance you'd need to be from the impact point all scale up accordingly. The distance rule still applies exactly the way it did in Video 1. Energy falls off with a square of the distance, so doubling your distance still cuts the impact on you by a factor of 4. You just need more distance to get the same margin of safety. There's an unusual silver lining specific to comets. Because they're made largely of ice and loosely bound rock and dust, comets are structurally weaker than solid asteroids, and they frequently fragment under the stress of approaching the sun or entering an atmosphere. Exactly what happened to Shoemaker-Levy 9 at Jupiter. A fragmented comet can mean multiple smaller impacts spread across a wider area instead of one single catastrophic strike, which, while still dangerous, is often more survivable in aggregate than one concentrated hit of the same total mass. It's not a guarantee, and a large enough fragment is still a serious regional threat on its own. But it's a real physical tendency this particular threat has that a solid asteroid doesn't. If a comet large enough to trigger global effects did strike, the aftermath looks exactly like the impact winter we covered in Video 1. Dust and vaporized material lifted into the upper atmosphere. Sunlight blocked for months to years. Crops failing. Temperatures dropping. The mechanism doesn't care whether the object that caused it was rock or ice, which means the same long-term survival architecture applies without modification. Decentralized food reserves, sunlight-independent agriculture, indoor and underground farming, and seed vaults like Svalbard, preserving the genetic diversity of our food supply through exactly this kind of prolonged disruption. This is the real advantage of thinking about these threats as a series instead of in isolation. The seed vaults, the underground agriculture, the decentralized food systems, none of that had to be reinvented for a comet. It was already built for an asteroid, and it works exactly as well here. Because impact winter physics doesn't check what kind of object caused it before it starts blocking out the sun. Here's what this episode really proves. 6 videos into this series. Every threat we've covered demanded something slightly different from us. Years of patience, 15 minutes of discipline, decades of quiet watching, or nothing at all beyond continuing to look. A fast-moving comet demands speed, and speed is uncomfortable because it means less margin for error than almost anything else on this list. But less time is not the same thing as no time. We proved in 2022 that we can hit a moving target in deep space and change its path. That capability doesn't stop working just because the countdown got shorter. It just means the readiness has to already be built before the clock starts, not after. That's the actual lesson of space won't win. It was never a promise that every threat gives us comfortable warning. It's a promise that comfortable warning was never the requirement. So there it is. The threat with the shortest warning window in the series turned out to lean on the strongest capability we've already built. Did you expect a comet to be more survivable than it sounds? Let me know in the comments. And in the next episode, we're covering something with more raw power, packed into a single moment, than almost anything else in the universe. A magnetar flare, unleashed by a dead star, with the most powerful magnetic field ever measured, capable of disturbing Earth's atmosphere from clear across the galaxy. If something like that ever erupted close enough to matter, would there be any warning at all? Or any way to prepare? Subscribe so you don't miss it. Space won't win.